Hello guys, welcome to this new video. So now we're going to go through question 2 in the May 25 Specimen Paper 2. So here we are told that a spacecraft is flying past the space station with a relative speed of 0.8 times the speed of light. And we have two beacons, R and F. And they emit light pulses at the same time according to the observers on the space station. And yeah, they are emitted 1,200 meters apart, measured by, again, the space station observers. So in the reference frame of the space station. So firstly, we need to calculate this gamma factor. And well, we can just use the equation that gamma is equal to 1 over the square root of 1 minus v squared over c squared. We are told that v is 0.8 c. So if we plug these values in, we will just have 1 over the square root of 1 minus 0.8 squared. So this will be 5 over 3, or approximately 1.67. Now, we need to calculate for the reference frame of the spacecraft the distance between the two light pulses. So, we know the distance between the light pulses in the space station reference frame was 1.2 kilometers, but now we need to calculate this for the spacecraft's reference frame, and we need to use the Lorentz transformation formulas. And well, in our data booklet, we have this formula that x prime is equal to the gamma factor times the distance in the original reference frame minus the speed times the time. And well, we want to find the distance and the speed, so we can just write the deltas for the distances and the times. So we'll get the equation that the change in the spacecraft's reference frame is equal to the gamma factor times the difference in the original reference frame minus v times the delta t. And well, we know that delta t is just 0. This is the time interval between the pulses in our original reference frame, so in the reference frame of the space station. So this will just be 5 over 3 times delta x. This is again in the reference frame of the space station, which is just 1,200 meters. So this will give us 2,000 meters according to the spacecraft. And then we need to calculate the time between the light pulses as well for the reference frame of the aircraft. And well, we have a very similar formula in our data booklet. And this is the gamma factor times the time minus Vx over c squared. And well, again, we want to find the difference in the time. So we can just put in deltas everywhere. So we'll have that the change in the spacecraft's reference frame time is equal to the gamma factor times delta t in the space station reference frame minus v over c squared times delta x. Again, that's in our space station reference frame, so this will be 5 over 3 times, well, again, this is just 0, as they're emitted at the same time according to people on the spacecraft. So this will just be minus 0.8 times over 3 times 10 to the 8. This would technically be squared, and then there would be another c, but this c would cancel out with this squared, as c is just also 3 times 10 to the 8, so we don't need to write that, and then we multiply it by 1,200. In our original reference frame, this will give us minus 5.3 times 10 to the minus 6 seconds. And then lastly, we need to determine which light pulse happened first. I'm obviously assuming we're in the reference frame of the spacecraft, although this is not the continuation from part B. It's like part C, but it wouldn't really make sense to calculate which happened first, as in the space station reference frame they happen at the same time. So we can just assume we need to calculate this for the space station's reference frame. So, well, we need to think about what this delta t prime actually is. This delta t prime is the difference between the two events. So it technically is just the time at which F happened minus the time at which R happened. The difference between these two events. So we can say like T prime F minus T prime R. And well, we know that this here is negative. from the previous part. So we know that this is smaller than 0. And so what we can say is that T prime F is smaller than T prime R. So this means that F happened at an earlier time than R, as the time at which it happened is smaller. So F happened first, according to the spacecraft. And well, this was the end of this question. I hope I was able to help, and see you in the next one.